Uh, we are continuing the lectures of carbohydrates, and in this segment we'll be discussing the ring structure of carbohydrates. I have already given you a preview of basic structure which is possible so far as monosaccharides are concerned, and now we will see how we can design the ring structures. As I have already told you, these carbohydrates, there are some monosaccharides, there are some monosaccharides which are having carbon 5 and carbon 6. They are stable in ring structure. They are stable in the ring structure. And the possible ring structures are, one is the hexagonal ring, which we call as pyranose, and second is the pentagonal ring, which we call as furanose. Pyranose has 6 carbons and 1 oxygen, and it is made up of, this ring is made up of 4 carbons and 1 oxygen, right? Let us see how I can put the open chain structure of glucose or galactose or mannose in ring form. For example, we recapitulate how, if we want to write the glucose, you have to write this way. This is 1, 2, 3, 4, 5 and 6. Here it is CHO, here it is OH, here it is OH, here OH, here OH, and in the last it is CH2OH. This is glucose. This is D-glucose, the open chain structure of D-glucose, right? Now, if we number it, it is 1, 2, 3, 4, 5, 6. Okay. Then you fill the valency of carbon, you substitute the valency of carbon by hydrogen. Wherever we have carbon unoccupied, we have to put hydrogen there, and it's very simple. Okay. By this way, we can form the open chain structure of D-glucose. Now, I have to put it in ring form. Probably you might have learned in organic chemistry. We have the formation of semi-acetal and semi-ketal. Okay, formation of semi-aldehyde and semi-ketone. Here what happens, this functional group is taking hydroxyl group of last but one carbon atom. Last but one carbon atom which has hydroxyl group goes with the functional group. That's all. We can design the ring structure. We have to remember only one point, that the last but one hydroxyl group has to go with the functional group, and then I can put it in the ring structure. Now the first thing is that this glucose is stable in pyranosic form or in furanosic form. I have already told you the stable structure of glucose is the pyranose ring. So when I have to first form the pyranose ring, glucose is stable in pyranosic form, and pyranosic ring is a hexagonal ring. This is a hexagonal ring. This way I can put the pyranosic ring. This is pyranose ring, right? Then I will put this structure. on the pyranose structure. See, first of all, we have functional group is CHO. It is O here. It must be C here. You can understand this is C, this is C, this is C, and this is also C, right? So we have CHO. It is CO, and we are missing H. For example, this is the H. This is a complete functional group. C, this is CHO, C, H, and O, right? And this CHO has dragged one hydroxyl group from the carbon number 5. Okay, now this hydroxyl group is attached to the COHO. So this hydroxyl group is attached with this CHO. So I can write hydroxyl group. Okay, so this is done. This CHO and OH we have already drawn here. Then let's move to, this is carbon number, this was the carbon number 1, this is carbon number 1. Let's go to the carbon number 2. In the carbon number 2, you have C, this is C, you have H, this is the H, and you have OH on the external side. This is OH on the external side, right? Move to the carbon number 3. Okay. In the carbon number 3, you have H outside and you have OH inside. Okay. Go to the carbon number 4. Let us go to the carbon number 4. We have OH outside and we have H inside. This is 4. Go to 5. Go to 5. Here in the fifth carbon, we have carbon. Okay, we have already mentioned it here. We have a carbon. This carbon is attached with hydrogen inside. This is attached with hydrogen inside. And you do not have this OH group because OH group has already taken by the functional group, right? Then this carbon has one more attachment, that is CH2OH. So we can write here it is CH2OH. And this is the carbon number 5 and this is the carbon number 6. This way we can write the structure of glucose. Understand? Now we can call this glucose as alpha D. I can name this glucose, the pyranosic form of glucose, as alpha. Why alpha? Because hydroxyl group is on the lower side. If the hydroxyl group would have been at this place and hydrogen will be having at this place, then we can call it as beta. But hydroxyl group is on the lower side, so we call it as alpha. D because it shows isomerism and it rotates the plane polarizer light towards the right. Therefore, it is dextrorotatory. Alpha D glucose. Alpha D glucose. This way I can write the glucose. Similarly, you can write other structures as well. If you want to see the structure of Manos, for example, we have Manos. Manos we can write this way: 1, 2, 3, 4, 5, and 6. This is functional group is CHO. Here it is CH2OH. I told you the difference between glucose and Manos lies at carbon number 2. If I want to write the glucose, OH is here, OH is here, OH is here, OH is here, right? This is glucose. But the difference between glucose and Manos is the difference lies at carbon number 2. Carbon number 2 and carbon number 2, the hydroxyl group is on this side. Okay, it is H here. Then I can substitute the values by H. I can fill the rest of the valences by H. This is Manos. This is the Manos. Again, if I want to put it as structure, it is also stable in pyranosic form. This Manos is also stable in pyranosic form. It is just like a glucose. It is stable. It shows its stability in pyranosic form. And the structure, when I will put the Manos in the pyranosic ring structure, it will be same as that of glucose with one difference. And what will be the difference? The difference will be at carbon number 2. At carbon number 2, there will be a difference. At carbon number 2, what we have OH on the outer side and H on the inner side. But so far as Manos is concerned, the OH is on the inner side and H is at the outer side. You can see it here. For example, this OH is going to be taken by the functional group. And what we have C, H, H, O, C, H, O, right? It has taken one OH group, OH is here. Then at position number 2, we have OH on the inner side and OH on the inner side and H on the external side. At carbon number 3, we have OH on the inner side and H on the outer side. 4, we have OH on the outer side and H on the inner side. And on the 5, OH has been taken by the functional group. We have C, H, H on the inner side and CH2OH on the outer side. Then this becomes alpha D Manos. It's not glucose now, it is alpha D Manos, right? So if we really remember the glucose, if we really remember the open chain structure of glucose, if we remember the open chain ring structure of the glucose, we can write rest all structures. We can put all the structures by manipulating some H and OH at some particular positions. It will be very easy for us to draw the other structures. This is alpha D Manos. If I want to make beta D Manos, I want to make beta D Manos, what I have to do? I have to put this OH on the upper side and this H on the lower side. This is the structure of beta D Manos, right? Okay. Similarly, you can make the structure of, you can make the structure of galactose. Galactose, again, you know it is 1, 2, 3, 4, 5, and 6. Here it is CHO, here it is CH2OH. Okay. The difference between, first I will make glucose again, OH here, this is the open chain structure of glucose. And what is the difference between galactose and glucose? The difference lies at carbon number 4. Let's move. 1, 2, 3, 4. At carbon number 4, there is a difference. That means the difference is the OH is on this side and H is on this side. Then this is all hydrogen, this is all hydrogen, this is all hydrogen. So here is a difference. Okay, I want to draw the ring structure of this. Again, there will be, for glucose, the OH was this, here and H was here, right? Again, if I would like to draw the ring structure of this galactose, where is the difference? The difference is at carbon number 4. I will move to the carbon number 4. The OH will be here and H will be here. That becomes galactose. This way we can draw the galactose. But so far as fructose is concerned, fructose has a different structure. We have galactose, we have Manos, we have this glucose. They are stable in pyranosic form. But when we talk of, because they have the functional group, that's CHO, that's aldehyde, and they are stable in pyranosic form. But when we talk of fructose, the situation is different. The fructose is the sugar which is stable in furanosic form, furanosic ring form, and fructose is the structure which has the functional group not an aldehyde, but it has the functional group which we call as ketone. Let us see. The empirical formula is C6H12O6. It is fructose for glucose, Manos, galactose for everyone. And see how I can put this fructose. Fructose has how many carbons? 6. 1, 2, 3, 4, 5, and 6. Right? It has the functional group that is ketonic. It is C double bond O. Right? Again, you draw glucose. 1, 2, 3, 4, 5, 6. I told you, if you want to make it easy, you always remember glucose. It is OH here, OH here, OH here, OH here. This is glucose. Now we are drawing here fructose. It is made of 6 carbons, right? And there is a functional group which is ketonic. It is C double bond O. And here, this must be CH2OH, and this also must be CH2OH. Right? Because C here, H here, and OH here. This is H2H. And see, after that, I have to see what is the arrangement of OH groups. The arrangement of OH groups is same as that of glucose. This is 1, this is 2, this is 3. 1, 2, 3, 4, 5, and 6. Let's move to the carbon number 3. The OH is on this side. Okay, it is on this side, right? On 4, it is on this side. It is on this side. Okay. On 5, it is on this side. It is on this side. Right. This becomes the structure of, I can say, fructose. This is the fructose, right? And in this fructose, what we have, we have some valencies which we have to fill with the hydrogen atom. This way we can fill it. This is D fructose. Now we want to put the ring structure of this fructose. And ring structure is not the pyranosic, but we have the furanosic ring structure. And furanose ring is a ring which is not hexagonal, but it is a pentagonal ring having how many carbons? Having 4 carbons and 1 oxygen, right? 4 carbons and 1 oxygen. See, I would like to make it. Again, I told you, so far as the pyranosic structure is concerned, I told you there is formation of, when there are aldehyde groups are involved, there are formation of semi-aldehyde, or you can say hemialdehyde. And here there is formation of hemiketone. The last but one OH group, has to go with the functional group. Then we can try it. See, at number 1 we have C. This is C. At position number 2 we have C. Right? This is C. This is the C and C. Okay. Then there is O. We have O. All right. This is C and O. Okay. This C is attached to, on one side it is attached to CH2OH. And on the other side, this CO has dragged the hydroxyl group from carbon number 5. I can write hydroxyl group here. Try to understand. Once we will understand this part, it is done. See, what we have C double bond O. This is the functional group, ketonic group. This ketonic group has taken the hydroxyl group from carbon number 5. Okay, this hydroxyl group is now with this C double bond O. And let me put this C double bond O. This is C here at position number 2, at position number 2. And this C is attached to the O, this C is attached to the O, right? And on one side it has CH2OH, on one side it has CH2OH, and also it has taken hydroxyl group from carbon number 5. It has taken hydroxyl group from the carbon number 5, which we can write here. Okay, then this must be 1, this is 2, this is 3, 4, 5. Okay, now let us see what is going to happen at position number 3. Go to position number 3. Hydroxyl group on the inner side, hydrogen on the outer side. Hydrogen on the outer side, hydroxyl group on the inner side. Go to position number 4. This is the fourth one. Hydroxyl group on the outside and H on the inner side, right? And go to the position number 5. This is 4, this is 5. Go to the 5. Okay, I'm sorry, there is some disturbance. See, let's go to the position number 1. This is 2, this is 3. Go to the 3. 3, we have hydroxyl group on the inner side and H on the outer side. Go to the 4. 4, hydroxyl group is on the inner side. Hydroxyl group is on the outer side and H is on the inner side. Okay, move to the 5. Move to the 5. At position number 5, we have C. And with this C, we have hydrogen which is attached. We have hydrogen attached on the inner side. Okay, and this C is also attached to CH2OH. CH2OH. This way we can draw the fructose. And I can say this is, whether this is alpha or beta, again I have to see the position of hydroxyl group. OH is here, I can say it is alpha. Alpha D fructose. I will call it as alpha D fructose. This way we can draw the structure of fructose. Okay, so this fructose is stable in furanosic form and I can put it in this way. This is fructose. So we have learned the structure of glucose, Manos and fructose. One thing I will tell you, what is a reducing sugar? What is a reducing sugar? Whatever sugars I have discussed, reducing sugar. Reducing sugars are those sugars which has a capability to reduce copper plus 2 to copper plus 1. This is the higher oxidation state of copper. We call it as cupric, which can reduce cupric form. This is the lower oxidation state to cuprous form. If I will tell you, if there is any sugar which is reducing, the reducing sugar has the capability to reduce the Cu plus 2 to Cu plus 1. It can reduce, it can cause the reduction of Cu plus 2 to Cu plus 1. This is the reducing sugar. And we have some sugars which are reducing, or we can say most of the sugars are reducing, but we have some sugars which are not reducing or which are non-reducing. How we can establish which sugar is reducing and which sugar is not? For that thing, what we need to do, we have to understand if the functional group of any sugar is free. If the functional group of any sugar, whether it is a monosaccharide, whether it is a disaccharide, whether it is a polysaccharide, if it is functional group is free, it is a reducing sugar. If it is not free, then it is a non-reducing sugar. Again, there is a question, how we can know whether the functional group is free or not. See, if we have to draw the glucose, for example, this is glucose, this is the glucose, this is the glucose, right? And here we have OH, and here we have H. This is the functional group. This is the functional group. And the functional group is not attached to any other group. Just see it. It is free. It has not made association. It has not made interaction with any other group. The glucose is completely free. And its functional group is also free. I can call it as a reducing sugar. And similarly, if I see the Manos individually, Manos has a free functional group It is not attached to anything else. It is a reducing sugar. If I will go to the galactose, if I will go to the fructose, if I will go to the ribose, any sugar, any monosaccharide. When I say monosaccharide, it is only a single sugar. It is single sugar. It has not made interaction with anything else. Any monosaccharide has a free functional group, and presence of free functional group makes it a reducing sugar. And a reducing sugar has a property to convert Cu plus 2 to Cu plus 1, yani cupric to cuprous form. It can convert the cupric form to cuprous form. We might have experimented in our labs. Benedict solution, phalanx solution. In Benedict solution, the Benedict solution contains copper, but copper is in +2 oxidation state. The Benedict solution has copper, and copper is in +2 oxidation state. That means it is cupric form. And when we put some sugar into the Benedict solution and heat it, what is the color of Benedict solution? The Benedict solution is blue in color. You might have done it in your lab. The Benedict solution is blue in color. But when we put some sugar, some monosaccharide like glucose, Manos, galactose, ribose, arabinose, xylose, glyceraldehyde, when you put the sugar in the Benedict solution and heat it, the color is changed to brick red. What is the color change? Why there is color change? Because color change is because of the fact that this Cu plus 2 has converted into Cu plus 1. And there is complete reduction because this sugar, once we add sugar to the Benedict solution, the sugar is a reducing sugar, and reducing sugar has converted the Cu plus 2 of Benedict solution to Cu plus 1, and which is indicated, which is represented by a color change, and color change is from blue to red. Okay, so this is this way we can sometimes I can say a very hazardous disease, a very chronic illness which we call as diabetes. And in diabetes we find one of the symptoms of diabetes is glycosuria. The patients are excreting the urine excreting the glucose through the urine. We have seen it. And because the renal threshold of glucose has exceeded, that's 180 milligrams per 100 ml of blood, right? So if we want to detect the sugar, I mean to say glucose in this case in urine, and what I have to do, I have to put the urine in the Benedict solution, and then we have to heat it. If the urine contains sugar like glucose, it will change the color. We can detect. We can simply detect by this small experiment. We can detect whether this urine has sugar or not. Normally urine do not have sugar, but only in case of diabetic patients there is excretion of glucose, right? This way we can call it as reducing sugar. So what I will conclude, all monosaccharides so far as we have discussed are reducing, but among disaccharides we have some disaccharides which are reducing and some we have which are non-reducing, and among polysaccharides we can say they have one chain, one functional group on one side which is open, and they are also reducing. We will be taking this once we will go to the disaccharides, once we will go to the polysaccharides. So that's all about what are the monosaccharides and what are reducing sugars. We'll be continuing next. We'll continue other lectures. Thank you very much for watching.